All right, welcome to this video. In this one, I want to look at how to balance a redox reaction in acidic media. So what are the steps that we need to take to balance this kind of reaction? So we're given an unbalanced redox reaction equation, and we're told this reaction takes place in acidic media. And you can actually see it from the fact that there is phosphoric acid present and other types of acids also present. So, and that should be a giveaway, but you'll generally be indicated in some way. Right. So what is the first steps that we need to determine when we're looking at a redox reaction and we want to balance it? We need to determine which species is undergoing oxidation and which species is undergoing reduction. So in other words, we allocate each species oxidation number. So the ones that we always know in this situation is hydrogen and oxygen, and the ones that are unknown are the chromium and the phosphorus. So let's start by assigning each of them their oxidation number. So in this first case, we have H3PO2. And what we know is that for hydrogen, the charge is always +1. For oxygen, the charge is always -2. And the phosphorus is unknown. So how we then check that is we say, well, for hydrogen, there's 3 hydrogens with a +1 charge. There is 1 phosphorus, so we give that an X, which we just want to solve for. You can call it whatever you would like to call it. You can call it oxidation number of phosphorus or whatever symbols you want to use. You're welcome to use. And then for oxygen, there are 2 oxygens and each of them carry a -2 charge. The overall charge of this species is 0 because it's a neutral compound. So this all should sum to 0. And therefore you get 3 minus 4, and then you should get that phosphorus or this X, which is equal to the oxidation number of phosphorus, is equal to +1. So maybe indicate to yourself that this is +1. We do the same for the chromium. Cr2O7 2-. I don't know why it's cutting off there. So in this case, what do we know? We know oxygen's oxidative number is -2. We want to determine what chromium's is. So hence we can go ahead and write, well, in this case, Y. There's how many chromiums? There are 2 chromiums, and we want to determine this Y for it. There are 7 oxygens with a -2 charge. And this needs to be equal to the charge on the species. And the charge on the species in this case is -2. So you can solve for Y. -14 goes to the other side, you get 12, and hence Y is equal to +6. So maybe write there for yourself, it's +6. The product side, H3PO4, again a neutral species. We know hydrogen's oxidative number is +1. We know oxygen's oxidative number is -2. And we want to determine phosphorus. So we set up the equation. It's 3 times +1 plus we want to determine that of phosphorus plus 4 times -2 needs to be equal to 0 because it's a molecular compound. Its total charge needs to be 0. Just in case you're wondering why I use X, Y, and Z. You don't have to. It's just actually for me to differentiate that the X is the phosphorus in the first compound, the Y is the chromium in the second compound, the Z is the phosphorus in the product, first product, and so on. So you can more easily differentiate. I want to write. So therefore, the Z is then equal to, well, minus 8 plus 3 goes to the other side. It's equal to plus 5. And the final compound, well, it's just chromium 3 plus. So chromium 3 plus, and that means, well, we can call it anything we want. So X, Y, Z is usually the one, but let's call it T is equal to plus 3. Okay, so in this case, the phosphorus is plus 5, and the chromium is plus 3. So because it's written there, chromium 3 plus. So you just read it off. Now we need to determine which species is undergoing oxidation and which species is undergoing reduction. The only species whose oxidation number is changing is the phosphorus and the chromium, right? Because you can see the chromium and the phosphorus are the ones that we determine. Hydrogen and oxygen's oxidative states do not change. We take them as given. So we can write therefore the phosphorus and therefore the chromium undergoes a change. The phosphorus goes from plus 1 to plus 5, and the chromium goes from plus 6 to plus 3. Hence, we can see the phosphorus has an increase in oxidative number, so there's an increase in oxidative number. Therefore, the phosphorus-containing species is oxidized. So this is the oxidation process. And we see the chromium's number decreases from 6 to 3. So it is a decrease in oxidative number. Therefore, it is part of the reduction reaction, the reduction half reaction. But what is the thing that's actually being oxidized and reduced? Well, the oxidation is the species of H3PO2, because we don't have loose phosphorus and we don't have loose chromium. So it's just the species that I was looking at. It's chromium 2O7 2 minus is reduced. H3PO4 is oxidized. All right. So let's write the half reactions. So hence the half reactions. The oxidation half reaction is the one where H3PO2 aqueous. Leave some space because we're going to balance them now. So you're going to add some stuff. Is oxidized to H3PO4 aqueous. Right, so that's the first one, and let's just write the reduction reaction as well. Reduction is chromium 2O7 2 minus the chromate anion. It's also in the aqueous state, and it is then converted to chromium 3 plus, which is also in the aqueous state. For now, you can leave the phases until the end. You just need to remember to add them at the end again. Maybe it helps in your writing or whatever. Right, so let's look at the oxidation reaction first. We need to find first for mass balance. So let's maybe make a little tick list here at the bottom. We want to balance all the reactions for mass. Then we want to balance them for charge. Then we need to look for overall balance. In our full chemical equation. And then we just need to remember to check our phases. Right, so that's our checklist. So let's start with the mass balance. I'm going to do that in red. So in this first half reaction, we see H3PO2 and we see H3PO4. So how do we balance reactions? We first look at the non-hydrogen oxygen species, then we balance hydrogen, then we balance oxygen. So that's our steps. So what's the non-hydrogen oxygen species? It's phosphorus. So we see there's one phosphorus there, there's one there. So that's fine. There's 3 hydrogen here, there's 3 hydrogen here. So that's fine. And then we need to balance oxygens. And there's 2 oxygen on the left and there's 4 on the right. Right, so now your first instinct might be to, I'll just put a 2 there. And then I get 2 times 2 gives me 4. But then what do? You mess up all the other stuff. And then you're going to put a 2 there. And then you see it's like an iterative process. So that's not going to work. Well, that way is not going to work. But what are we in? We are in aqueous acidic media. So what is something that we can use that is in acidic media, is available, that contains oxygen that we can then do something with? And of course, that means it is water. We have 2 sources when we're in acidic media. It is water and H+. There's protons floating around because we're in acid, and there's water because we have aqueous conditions. So water can be a source of oxygen and hydrogen is, of course, a source of hydrogen. So that one is quite easy. So since we want oxygen, we need water. And water is, of course, a liquid. And how many oxygens do we want? We want 2 oxygens. We want to say 2 times 1 gives us 2 additional oxygens in this situation. So now the oxygens balance. But what have we introduced inherently by introducing water? We've introduced hydrogen. So now our hydrogens no longer balance. But how do we balance hydrogens? Well, the easiest way is to add hydrogen plus on the other side. Hydrogen plus is going to be aqueous. And how many hydrogens do we need to add? There's 2 times 2 hydrogen. So that gives us 4H plus that needs to be added. All right, so that's our oxidation half reaction balanced according to mass. We can just quickly check it. H3 or P and P still the same. H3 plus 4H gives us 7. 3 plus 4 is also 7. Oxygen, there's 2 here, there's 2 there, there's 4, and there's 4 on the right hand side. So that's mass balance for that one. So we can go and put mass for the oxidation reaction. Now let's do it for the reduction reaction. So in this case, we have 2 chromiums on the left-hand side. So there's our 2 chromium on the left-hand side. And we have only 1 chromium on the right-hand side. So our first step will be to put a 2 there, because that's the only place where chromium can be balanced, is in that. There's no chromium available in water or H+. It's the only place the only source of chromium is that. Next question is, so we have oxygen on this side. So we need to produce oxygen on the other side, and the product side. But how do we produce oxygen? It's via water. Water is our only source of oxygen in this situation. So we introduce water on the product side. Right. Now we can balance the water. So there's 7 oxygen on the left-hand side. There's 1 oxygen on the right-hand side. So it means we need 7 water to be produced. But by introducing water, what do we inherently introduce? We introduce hydrogen. And there's no source of hydrogen in the chromium, so the only place that we can add hydrogen is, or in acidic media, you always balance using the hydrogen. So we introduce hydrogen plus, it's in the aqueous state. And how many hydrogens did we introduce here? We introduce 7 times 2. So we need 14 hydrogens. Right. And is it balanced now? 2 chromium, 2 chromium, 7 oxygen, 7 oxygen, 14 hydrogen, 14 hydrogen. So yes, we've balanced according to mass both our half reactions. So what's our next step? To balance according to charge. So let's look at the total charge. Both of these species have a 0 charge. So in other words, our total charge on this side is equal to 0. So we do not need to do anything. Well, we just need to look at the other side as well. This species has a charge of 0, but this one has a charge of +1. So then 4 times +1 means we have a +4 here. So the total charge is equal to +4. And what is the only thing that we can introduce to balance charge? That is electrons, because adding hydrogens on the left-hand side would not make sense, because then they just destroy it again. Because if I were to, for example, add 4 hydrogen here, they would just cancel with one another. And then we're left with the unbalanced mass again. So it doesn't make sense to go that route. So the best thing to do in this case is then to say we add electrons. And on this side, so this side is 0, that's fine. This side is +4. And electrons carry a charge of -1. So how can we then balance the right-hand side? We need -4. So that implies 4 electrons that we need. So we add here 4 electrons. That will balance the +4 charge. So then we get a total charge of 0. So now we have total charge of 0 on both sides. Let's change that color to a green. Okay. So now our half reaction, our oxidative half reaction, is balanced according to charge. We need to do the same for the reduction half reaction. So what is the charge currently here on the left-hand side? Well, it's -2, or 2 minus, that's too thick. So it's -2 total charge. It's currently equal to -2 plus 14 times 1. So 14 times +1. And that gives us a current total charge of 12, plus 12. What is our total charge here on the right-hand side? Well, it is 2 times +3, so it's 2 times +3, and 7 times 0, because this is a molecular species, so it doesn't carry a charge. So our total charge here at the moment is +6. What is the only thing that we can introduce to balance charge? It is electrons. So electrons carry a minus charge. So which one needs to become smaller to match the other one? So which one is larger? At the moment, our left-hand side is heavier. So we need to get 12 to 6. And we can do that by adding -6. So in other words, we need to place here 6 electrons on the left-hand side. Okay, so now this one is also balanced according to charge. Right, now the final step, I say final step, but like the next step is to then write, what color do I want? Let's use orange. To sum these two equations. But in order for us to sum them, we need to balance the number of electrons first. Because if your number of electrons are balanced, then you'll sort out your equation quite easily. or they'll sum up to the correct numbers. So we have 6 and we have 4. It's a bit of a difficult one. The question is, what does both of these equations need to be multiplied with to get a common number between 6 and 4? So 6 and 4's common denominator, you might want to say 6 times 4 is going to give 24, which is fine because it will sort itself out. But the lowest number that both 6 and 4 divides into is 12. So you start with 6 times 1, 4 times 2. Okay, that gives 6 and 8. That's not right. 6 times 1, 4 times 3 gives 12. Okay, so in other words, how does 6, this one you multiply, so you said it's 12. Then you divide it by the number here. So this one needs to be multiplied by 2. And this one needs to be multiplied by 3. Right. So now we add them, and we need to remember to do the multiplication. So let's start by adding the reagents. And so the first one, H3PO2, then we'll have 3H3PO2 in the aqueous phase. And where do I get that from? We say here multiply by 3. So this 3 is multiplying each of the stoichiometric coefficients. So each of these numbers will be multiplied by 3, each of them. Okay, so that's 3H3PO2 aqueous phase plus, so we have 2 times 3, water, so it's going to be 6 water. It's in the liquid phase, and there's nothing else on the reagent side. Okay. On the redox side, we need to multiply by 2, so we'll have plus 2Cr2O7 2 minus aqueous plus 28H plus aqueous. And I'm going to add the electrons, even though we know they're going to cancel, but we just double check ourselves. So 2 times 6 gives us 12 electrons. That's the reagent side. So let's look at the product. We should get 3H3PO4. It's in the aqueous phase. Plus 12H plus. So it's 3 times 4. Aqueous phase. Plus 12 electrons. Also on the product side, we have 2 times 2 chromium 3 plus. That's 4 chromium 3 plus in the aqueous phase. Plus 2 times 7, so 14 water in the liquid phase. Okay. Now, how do we check for or simplify our equation? So that's technically this overall balance is simplification. So you can add here for yourself also and simplify. So to simplify, so we start on the left-hand side. We ask ourselves, what do we have? We have H3PO2. Does H3PO2 appear on the product side? No. So that one is fine. There's 6 water. Is there water on the right-hand side? Yes. So in other words, we need to do something about that. And the side that has more is the product side. It has 14. The reagent has 6. So that means we're left with 8 water. All right. Next species, chromate. Is there any chromate on the right-hand side? No. hydrogen, so H plus protons. Yes, there's protons on the left-hand side and on the right-hand side. The left-hand side is more. So 28 minus 12 is 16H plus aqueous. Then we have electrons. We have 12 electrons on the left-hand side, and we have 12 electrons on the right-hand side. So they cancel. And that is what you should get. If you don't get that the electrons cancel, you did something wrong. All right. And then the other species also don't appear. So we've checked all of them. Check that one, check that one, check that one, we check that. Okay. So now we're just going to rewrite it because this is kind of a mess at the moment. So we now have 3H, 3PO2 in the aqueous phase. There's no water here, so the next thing is 2Cr2O7, 2 minus in the aqueous phase. There was 16 protons left in the aqueous phase. There's no electrons, so we then write our products. 3H3PO4 is also in the aqueous phase. Plus, the hydrogens cancelled, the electrons cancelled. So the next species is the chromium 3 plus. And there's 8 water left. Okay. So that is simplified. It's simplified. Now we just need to check overall mass balance. So we start with all the non-hydrogen and oxygen species. So we have one phosphor, there's one phosphor there, so that's fine. Then chromium, we have 2 times 2 chromium, and here we have 4 chromium, so those are fine. Do we have anything else left? No, so next we check hydrogen. So here we have 3 times 3, so let me just write that, so that's 9 hydrogen there. We have 16 here. We have 9 hydrogen here. We have 8 times 2, which gives us 16. So that's 25 on both sides. So yes, that's fine. Oxygen, we have 2 oxygen here. We have 2 times 7, so 14 oxygen here. On this side, we have 3 times 4, so it's 12. And we have 8 times 1, so we have 8 oxygen here. So, oh, sorry, not 2, that's 3 times 2 here. So that's equal to 6. So there's 6 plus 14 is 20. 12 plus 8 is also 20. So all our oxygen balance. Apologies for that small mistake. Right, so we have overall balance and we have simplified the equation. The last thing to check is just that we've written all our phases. So we have a phase there, phase there, we have a phase there, we have a phase there, phase there, phase there. And in our half reactions, we also wrote all our phases. Okay, so we have all our phases. And that is the balanced equation, given what we were given. If we were, for example, given potassium 2 here, and the potassium appears on the right-hand side, you would have had that it's some case or something, then you would need to add the potassium, but in this case, you were already given the iron, so you don't need to worry about that. So if there's spectator ions, then you include them. If it's asked for the full overall balanced equation, if it asks for the net ionic, or it gives you something that contains an ion with a species already, then you need not include the spectator ions. Then you can just write it as such. Okay, I hope this was useful. It was very painstakingly slow and going through every step, but I think it's useful to remind ourselves of all the little steps and all the little things that needs to be done. All right, thank you for watching.